All right, everybody. Thanks for coming to the talk. Using WebAssembly now, it's easier than you think. No, it's the end of the day here, so we're gonna try to make this pretty exciting. We really appreciate you sticking around for the last slot. I think we'll go ahead and just get into a little introduction. My name is Townsend. I'm a lead software engineer at Cosmonic and a maintainer of the open source project Wasm Cloud. Been working on that for the last 3 or so years, server-side WebAssembly, serial open source contributor. I really enjoy working with, kind of my weird trifecta is Elixir, WebAssembly, and Rust. Fun technologies to work with. And I'm a demo enthusiast, as you'll get to see today.
Yeah, and I'm Taylor Thomas. I am a director of engineering at Cosmonic. We at Cosmonic are working on a WebAssembly-based platform as a service. And I am a Rustacean by way of being a Gopher. Rust is just my favorite language. I code in all sorts of languages and things right now. I'm the co-creator of Crestlet, which was one of the first projects that was trying to do WebAssembly with Kubernetes. And as part of that, I've been involved in the Kubernetes space for a long time, and including being a Helm maintainer. And I'm also an open source maintainer of a bunch of different projects, including Wasm Cloud. So with that, I just want to go over our agenda and what we're going to talk about today. We're going to kind of start off with this, like, what's a Wasm? Just to cover that for those who might not know. And then where does it fit in? And then we're going to really just start talking about demos and what you can do next after you see what we're doing with these demos. These demos are meant to be very practical and real. You'll get to see some really cool stuff. And the whole goal is to show you all that WebAssembly, it's really in the title. Like, we're trying to show you that you can start doing this stuff now. This isn't just some magical future. So we're trying to show that with what we do in this talk. So before we talk about this, I'm just curious, how many people have not just read about WebAssembly, but used WebAssembly in some way? Okay, a few hands, that's good. Some of you may have been, I actually know some of you in here were at my talk yesterday at Kubernetes Community Day. So some of this will sound familiar because I'm going to be level setting the same thing. But we're going to just talk about what is WebAssembly and why it actually matters here to start off. Now you'll notice that the phrase here on top, any of us who've been speaking about WebAssembly for the past few years, you've probably seen this. The funny thing about WebAssembly is it's neither web nor is it assembly. So who knows? We have that name. But that's the whole point of why we're talking about it. Like, why is it called it? I don't really know. It came from Wasm. There's some stuff before, like, became Wasm. There was some stuff before that that I could talk through, but that's not important. What we're going to start off with is that it is an open W3C standard. So all these things is what makes it great on the web. So we like our standards, right? So all the browsers can interop. We also want something to be safe and secure. So this is, in WebAssembly, it's a completely sandboxed environment because that's what you need in the browser. It uses a capability-based model, which is the thing you expect to see nowadays, where it asks for permission to use your mic, permission to use your photos, permission to use your location, permission to all those things. That's capability-based. You have to explicitly grant permission for it to do things. It's also extremely efficient and fast because you're working at almost native execution speed, and it's very small. We're talking super tiny. We'll actually talk a little bit about those sizes in a second. But it's also polyglot. Most languages can compile to WebAssembly, especially for the web at this point. And it's portable, right? You're not going to have a browser technology that only works on Linux or only works on Windows. You have to have something that works across everything. And so it matches all these, it has all these requirements, and that's why it was such a fit for the web at first. So with that said, if you think about it, those 5 things that are listed here, they are the exact things we want for cloud native applications, for things running on servers, right? We want something that's standards based, right? That's why the CNCF exists. That's why the Linux Foundation exists, is because we want open standards we can work from. And so that's a very critical thing here. It's also very important that we have safe and secure code. And in particular, this is around the idea of, like, well, we have things like Docker, but how do we make it even more locked off, right? Especially untrusted code. We're all running either untrusted code or code we're not entirely sure. Like, even developers of our own company are technically untrusted code sometimes, depending on your company. And so having something that's entirely sandboxed is very, very good for that use case. Now, the efficient and fast is very, very important. If you've looked at, like, what happens with people, especially using Kubernetes clusters, but it also happens like running Docker or anything like that, Kubernetes clusters in our surveys of people are running about 25 to 35% utilization. And when you're using even just plain Docker or just other processes, you're not fully utilizing the total capacity of your machine. Now it's really hard to get to, like, complete 100% usage like that and safely. But what it does allow you to do is run it, a lot of them all on any device. So on a laptop like the one we're presenting on, we're talking about 3,000 to 6,000, depending on which things we're running, WebAssembly modules. So basically 3,000 to 6,000 binaries that are all running simultaneously on one of these machines. It's very, very lightweight and small. And size-wise, I can talk more later, but we're about 10% of the size of an equivalent Docker container. We're talking just a few megs at most of the time. And so you get very small size on disk and very small runtime size. It's also polyglot. It works for most languages. We'll talk about some of the weaknesses in a second. And it's portable. Unlike a lot of technologies that are used in the cloud native thing, this is the cloud native track, that's why I'm bringing this up in particular, is that Docker is not truly cross-platform. And we'll talk more about that in a second as well. But those things are all very important. Having something that runs across any operating system, especially as we start to get people creating their own processors, AWS Graviton, all the different cloud providers are making their own. All those different things are now in existence, and we have to be able to work in heterogeneous compute environments. So let's talk about this is what can you use it for? What is it good for? What is it not good for right now? So good on the left, bad, I'm using that term very loosely, on the right. It's very good for general server-side computing, namely true microservices. And what I mean by true microservices are not that Java app you lifted and shifted and is 20 gigs big and uses 16 gigs of memory. That is not what I'm talking about. I'm talking about true microservice patterns where you have, here's my user service, here's my photo service, here's my transaction service. That kind of thing works very, very well in WebAssembly. Also functions as a service. If you look at things like Cloudflare, Fastly, all the people who have started to have kind of these workers or functions on the edge, those are all WebAssembly based because, once again, can support pretty much most languages and then just compile straight to WebAssembly. The other thing that's really, really interesting about WebAssembly that I always call out because it's hard to show in a demo is the idea of runtime optimization. When you need to optimize your code right now, you have to do that at compile time and for the specific system you're on. With WebAssembly, you're actually able to do this at runtime. You have all your normal LLVM style optimizations that happen, but at runtime, you can choose whether you're going to use JIT, AOT, interpreted, which runtime you're going to use. There's a plethora of runtimes inside of the WebAssembly space, and all of them can run the same WebAssembly module. They just run it with different performance characteristics. So it's a pretty awesome thing you can do in terms of performance tuning. The other thing I'm going to put here is constrained devices with big, huge air quotes of the edge, which means nothing anymore. But the edge in this case, I'm meaning all the devices that do not fit well into your normal data center inside of a cloud region or whatever it might be. We're talking things like power stations, cell towers, those kind of things. Those are the kind of things I see as the edge. And also the constrained smaller devices that you see points of sale, things out in store locations, that kind of stuff. It works very good because, once again, it's entirely cross-platform and it's way smaller. You don't have the overhead of containers, and because you're able to write this once and run it everywhere, closer than you ever have in the past, because it is a compile target. Also, great for plugins. I personally am hopeful and believe that WebAssembly is going to be the last plugin model we're ever going to need. There's some stuff around the component model, which I'll be talking about in a little bit, that allows this to be even easier. But basically, you can just write your plugin in whatever code someone's comfortable in, rather than doing this gRPC contract or standard in, standard out, or whatever it might be. There's all these different plugin models. But this one makes it so you can essentially run it close to native code. It's also very good at libraries, which I'll explain more with the, like I said, the component model stuff down the line a little bit. And then, of course, it's great for the browser for very heavy compute applications. Think AutoCAD, Photoshop, Figma, those kind of things are all using WebAssembly in the browser, and it's very, very good for that. Now, that's the good stuff, the stuff you need to keep an eye out for. First things first, networking is still difficult, particularly for server side. We're just getting socket support landing for real, and so you have to be able to work around that. And that kind of leads into the second point here, which is we're in that fast moving mode. So things are breaking fast. If you're not very tolerant to quick moving things, if that's not in your risk that you can take, WebAssembly is a little bit moving too fast right now for some of those use cases. It's also, I think always, but I think we can continue improving it, it's going to be slower than native code, which makes sense because you're still compiling this down essentially to an intermediate target that then runs. That doesn't matter really. If you're running this in a network, the network penalty is much worse than any speed penalty from not running it native. So don't worry about that if that's your use case. But if you're talking about like performance tuned code, it's going to be a little bit slower. And then the tool chains just aren't there yet for some languages. To be perfectly blunt, you're not going to see Java that's not very smoke and mirrors hacky for a long time, I think. It's going to be a few years at least for that. But other things like JavaScript, Python, Lua, interpreted languages are coming along really nicely. Garbage collected languages are coming along real nicely. All of those things can start to compile to WebAssembly. But it does mean that there is no lift and shift with WebAssembly for a lot of use cases right now. And then, honestly, some domains aren't a good fit yet. They might be in the future, but now they aren't. Like I mentioned, performance-tuned applications, probably not the best fit right now. Another big one is I couldn't come up with a good catch-all for this, but like well-established applications. And I don't mean that as like a pejorative. I'm saying like think things like Nginx and Redis and MySQL and all those types of things where no one's going to go rewrite that so it can like compile down to WebAssembly. Somebody will try, I'm sure, but like for real, turn it into WebAssembly, that's not going to happen right now. So just keep that in mind, like that's not what is going to be its strongest use case at this point. So I mentioned this thing about Wasm Cloud here at the beginning, and Wasm Cloud is an open source project. It's hosted in the CNCF. Both Brooks and I are maintainers, but I wanted to ask this question of like, well, I just explained all these great things about WebAssembly, then why do you need something like a Wasm Cloud to exist? And the main thing here is the difference between a runtime and an application runtime. A runtime is something like Docker, or you're thinking Node versus, or like JavaScript versus React, or Node versus React. There's things that allow you to run code, and then there's things that allow you to build applications on top of it. Docker versus Kubernetes, I don't know if I said that one, but those are the kind of comparisons here. There's plenty of runtimes. There's ways to run this code, but there aren't ways to actually write applications and then run those applications. And Wasm Cloud does that in a very distributed way, which we're going to be showing you here in just a second. So with that, I'm going to let Brooks explain a little bit more about how we're handling this.
Yeah, so just kind of pick up where Taylor is leaving off here. Wasm Cloud is one of the many WebAssembly like higher level runtimes than just a WebAssembly engine. And the first and foremost thing that the project does is run and orchestrate WebAssembly. If you're coming into the space, the primitives, the low level primitives of like a WebAssembly engine, instantiating instances, importing and exporting functions to just take numbers, those kind of things are going to be lower level than you really want to work with when you just want to build an application. And so anything that's higher level is going to take care of that for you. We also provide the secure access to capabilities and take a little bit of an opinionated approach to this. So a true capability in like the white paper sense is like a file socket or like a network socket. But we think of capabilities like higher level application capabilities, your HTTP servers, the ability to make requests, the ability to access a database, kind of the same thing like when you open up a browser and you go to a web page and it says, hey, can I access your microphone? Those kind of things work really, really well for general user cases, and we think it applies really, really well to application development as well. Now, these WebAssembly modules, we call them actors, very similar to an actor model, but that's kind of all internal. Really, what we manage is you can horizontally scale multiple Wasm Cloud runtimes or vertically scale a bunch of your actors so that you're running a bunch of different copies of essentially a microservice. And we also manage the networking, the failover, the request routing, all the things for actors to communicate between each other or with different services. Those kind of things really drag on the experience of developing an application. You can spend a long time configuring that without really even touching your business logic. Now, we're talking about this in the cloud native track. We have been working on this runtime for a couple of years now, and we've really tried to reuse existing standards and things that work really, really well that people use in applications today. Things like the Open Container Initiative. This is how we distribute our WebAssembly modules. We don't stick them in a container, but we distribute them as OCI artifacts. The standard works really well for that. We use the open application model. It's a YAML format, and it also works with JSON, I guess. But for our declarative applications, people are very used to writing deployment specs like that for Kubernetes. We use cloud events for all of the kind of reactive things that happen in our system. Our networking layer is using NATS, which is a CNCF incubating project, which is, what is their slogan? It's connective tissue for all things distributed, something like that. And we also integrate completely with OpenTelemetry. All of our SDKs, the Wasm Cloud host, you essentially just add an OTLP exporter and we can export traces for everything in your system, which is huge for distributed systems and getting a concept of what's going on. So we've really been building on top of existing standards in order to make it as easy as possible to build WebAssembly applications. Now I'll dive into a few of the key concepts of Wasm Cloud, which I mentioned actors, and I mentioned actor model, and when you hear that, you either haven't used it or you have a pre-existing experience with something like Akka or something like Actix, and really a lot of the internals of the actor model are taken care of inside of Wasm Cloud. The really important thing that I want to talk about is because WebAssembly essentially has to ask the host for everything it needs to do, ask for all those capabilities, we find that really works well with a capabilities-based model where you design your actors in terms of contracts, like a contract-driven development. So instead of importing libraries directly, you work with an abstraction of a database or an HTTP server. And that means that you're not copying and pasting code, you're not worrying about how you're actually getting requests there and back. And I'll show a couple of code examples in a little bit just to tell you what I'm talking about. These are really easy to develop, low boilerplate. This is essentially what you're going to be writing when you develop applications. Now the capabilities, been harping on this. These are really, the important thing about these is that you can choose the implementation of your capability at runtime. You code your application in terms of a contract, and then whether you're working locally in development, you might use a certain implementation that's easy to run on your machine, deploy to production, you use your real production database, things like that. And this is all really decoupled from your application itself, and where many vulnerabilities, like when you think of log4shell, log4j, where it's a logging library that you import into your application, you compile it all in and deploy it because you need the non-functional requirement of distributed logging. But really, that's not making your application work any better or actually do what you need it to do unless you're just making a distributed logging library. And these kinds of vulnerabilities can happen all across like thousands of different applications in the same way. So decoupling that really abstracts it into the platform, makes it a lot easier to deal with that kind of management. And last but certainly not least, we call our network the Lattice network. It's a flattened topology network which really enables you with NATS to join cluster members at runtime, add and remove things, dynamically fail over to available compute. It really doesn't require any work on your part from the application developer side to have this kind of mesh network. And I always use mesh really carefully because it's not like a service mesh where you have to manage it and set it all up. It really just works. And I'll show you a couple good examples of how this works in a second. And now I always like to bring this up at the end of explaining what this open source runtime is like, because I want to talk about where this fits into the cloud native landscape. And over time, we've kind of seen this trend of abstraction, where we're removing the tightly coupled nature of applications from a computer and further abstracting things away from the actual hardware. So where you may have taken an application and like imaged a PC to run with it, then we had hypervisors to provision VMs and then containers on top of that, which essentially makes up the way that public cloud works today. And where WebAssembly really makes this interesting is we have a truly platform agnostic binary. It's not a container that pretty much mostly works on Linux or works in a Windows container, and if you need to run it on different architectures, you have to use like a BuildX, compile for different platforms. It is truly platform agnostic, and that's really powerful for the fact that I can develop something on my Mac, and then I can deploy it to a cloud, and I don't have to worry about what the architecture in OS is. That's huge in and of itself. The other big thing about WebAssembly is the deny by default sandbox. Anything that you're going to do other than do little computations in memory, you have to ask the WebAssembly host for. This is the same if you're in a browser, you're asking like Chrome V8. If you're on the server side, you're asking Wasm Cloud for, hey, can I make this HTTP request? It's all denied by default, and that's a really powerful model for where today we really like to layer on levels of security and add automation for patching, when really we could just remove that from the start. The biggest thing that adds on here at the end and where Wasm Cloud fits in, and this is of course an opinion that we're taking, is the abstraction of libraries from your application. So actually taking those open source libraries, the untrusted code, pulling it into the platform itself, having a platform team manage it, and the people who develop applications, they do so in terms of common contracts, and that can kind of be dynamically swapped out at runtime. So I really like bringing this one up. I know that the question can come up like, what's the difference between Wasm and Wasm Cloud? And hopefully this kind of illustrates some of the usefulness of WebAssembly on its own, and then the kind of what the project is doing. And with that, I think we are kind of at the end of the day. It's getting a little boring to look at slides and have us just talk at you. So why don't we show you some things for real, for real. So what I'd like to, I actually did have one more slide I wanted to show, and this is going to look a little familiar if you saw Taylor's talk yesterday, but I want to start with a small, pretty digestible example. This is a true microservice. We have the business requirement, and business, I don't know what you do when you go into work as an engineer, to take HTTP requests from some source and then increment a counter in some data store and then return that new updated counter. Tiny, tiny microservice, just updating a counter and persisting data. But really, the ability to take HTTP requests and store things in a key value store encompasses a huge subset of those microservices. Now, when you kind of blow this up, when you look at this from the Wasm Cloud perspective, there are a couple key elements that make this up. We have our business logic, which is just, I'm getting an HTTP request, increment number, return number. Easy. And then we have the things that are kind of more part of the platform, the capabilities, the HTTP server or key value store. And this is kept abstract really on purpose because locally I may be working on my computer, I just use like a hash map for my key value store. Easy, in memory, don't even worry about it. But then I deploy to an actual QA or something, this microservice, and I may want to store it in Redis. Or I may want to store it in DynamoDB because that's what my company uses. That implementation can be changed at runtime. So let's take a look at what this code actually looks like. So this code is going to be it's actually in Rust, which you may not have, maybe used. Actually, who's used Rust before? Who's actually looked at some Rust code? Nice, small subset of the room, but this should actually be pretty easy to grok just because there's not really much going on here. This is the entire WebAssembly module. It's written in Rust, compiled to WebAssembly. So we have one trait, which you can think of this kind of like an interface in other languages as an HTTP server, the abstract representation of handle requests. So we receive an HTTP request object, return an HTTP response. Really, like that's the most generic HTTP server. We're not picking a library at this stage. So I can actually grab a couple things like the method and the path that's made for the request, but really the big part of the business logic that's going on is this increment counter function, where we get a key value sender. We're saying, hey, we're going to send this request to a key value store. Please increment the value at this key by 1, and then return the new response as a JSON object that's a counter. This is probably not that special looking. It's a tiny little service, but the key thing is here, I'm not picking an implementation of a database, I'm not worrying about how to actually receive this HTTP request. All of that is handled by the capability at runtime, and I don't have to program any of it in. None of this is relating to networking. I'm calling all these things out because the demo is going to be pretty fun here. So let's take a look at this actual application running. I've got this nice little visualization in Cosmonic, but this is really just a user interface. I've got my single KB counter. I've actually got 5 replicas of it running. This is my KB counter WebAssembly module. I have an HTTP server that's actually running on my laptop here at the conference, and a Redis key value store that is also running on my laptop. I just have like a local Redis server running. And if I hit localhost 8000, I can actually see this nice little beautiful UI. I can increment the counter, I get the new number, it's all great. And all this UI stuff is actually in the code. You can see like we have a different handler for the static assets, all that stuff. But the point is we have our little microservice. Not a lot of code, pretty easy to understand. So let's talk about, you've gotten to this point and you've developed this little app. Like, what does it actually look like to get this WebAssembly module into like a production style environment? We hook it up to a real persistent database. You have a public endpoint that you can hit, all those things. Well, let me show you. And the point of showing you the things that I'm going to do is probably not the way that you're going to deploy a real application, but the point is to just show how flexible this kind of model is. So the first thing that we need to do is make sure that we can hit this WebAssembly module from a publicly accessible place. So let's go ahead, and we actually have this flexibility to change capabilities at runtime because of what we call links. You can see these links represented here on the user interface. So I'm just going to drag another link from the HTTP server to the hosted HTTP server in Cosmonic. This allows us to create a public DNS endpoint, all those things. And I'm going to go ahead and link those together. Now, we have a concept of what we call a wormhole. Very fun space theme. It's just an ingress point into this application. And if we access that, we can actually see kind of the same thing. Doesn't really look that much different. I'm going to go ahead and open up this QR code generator just for fun, because you can actually hit this application as well. I'll give you just a second while I stand here and spiel for a little bit. But this is going to come into play and be kind of fun. So pull this up on you can pull this up on your phone if you like.
And I wanted to point out that what we're showing you in Cosmonic is just for the UI. Everything here you're seeing can be run 100% open source. We're just using the UI, the pretty UI, for visualization purposes. So everything you see here is actually easily runnable. You can do it on your own. You can run this exact example on your laptop right now if you want to.
Yep. And so when you actually hit this endpoint, it's hitting an HTTP server. And if you have a quick question, that's fine, but we're going to take questions at the end. You're actually hitting this HTTP server and then tunneling that request down to my laptop to invoke a WebAssembly module and hit that Redis database, all that fun stuff. Woo. So I'm going to go ahead and hit this again. Whoa, nice. It looks like a couple of you are actually hitting it. Cool. I went up like 300 there. That was a little more than I expected. But cool. So, we're hitting this request going all the way down to this Redis database. That's great.
And note that it's a Redis database on his laptop that you're hitting from there through an endpoint that's sitting in US East.
Yeah,
So
I don't even have it. It's like in the background. I don't know where it is. Yeah, sorry. I didn't mean to cut you off there, Taylor. All right, so now really the next thing that we need to do is I'm running this WebAssembly module on my laptop. That's not really an extensible way to deploy something to production. So let's deploy a couple more copies of this, and let's put it in the managed host that's here on Cosmonic. We'll do 5 more instances or something. Now, this WebAssembly module, the really cool thing is I'm about to run a few more copies on an ARM Linux device. This local MacBook is one of the ARM MacBook Pros, so it is, same architecture, different operating system, but it's deploying the same artifact from OCI. And the really cool thing is that that doesn't need to change. Nothing in the application needs to change. So I deployed a couple more copies, and this is essentially just going to geolocation round robin between these instances. So if we look at that counter again and we hit increment, okay, somebody's hitting this a lot. I love it. We can see that everything works the same. Great. Now what we need to do is really this doesn't need to be hooked up to my local Redis database anymore, right? That's really not an extensible model. So I'm going to go ahead and get rid of this link between that and the local Redis database. And if you go hit the application right now, it's not going to work. It's going to return 0 or whatever. That's really fun. Now I'm going to go ahead and link this back up to a built-in key value store. This is essentially simulating an environment where you're using like a managed cloud provider key value store. You can use any implementation for that. And as soon as we hit refresh, you see a different counter. And that's a different counter because it's an entirely different database. And the cool thing is I've just taken that whole little app that's running on my local machine with all local assets and flexibly swapped that to a cloud running environment. And I can even come back into this visualization. I didn't really touch on this part yet, but I can find my laptop device where I was running everything before. And I can completely terminate this. That's the right one, right? Yep. I can terminate this out of the cluster entirely, and everything continues to work just fine because everything, of course, is now in the cloud. I can unplug, and you all can hit that. So really, like I said in the beginning, this isn't how you would deploy something to production. It is to show the flexibility of using different implementations for capabilities. It's the flexibility of WebAssembly to be able to spread across different devices without worrying about deploying to different architectures. Really fun stuff. All right, so we've touched a little bit on what's WebAssembly, what's Wasm Cloud, where does it all fit in? And you may be wondering, like, what does this look like? You know, am I just using Wasm Cloud specific assets to make this work? You know, are we hiding a lot of magic behind the scenes? And there's a lot of work going on in the standards bodies in WebAssembly right now to really take this to the next level and make it all a standard. So I'd love to pass to Taylor to talk a little bit more about that.
So I just wanted to mention this again. This is the components thing I was talking about. What we're doing right now, what we showed you, is distributed across, it's the distributed level. We're able to run your application in a distributed way anywhere, like Brooks was just showing. But there's work to be done and is very much crystallizing right now in the WebAssembly community called the component model. And the component model focuses around interfaces, but at the code level. So we're doing it at the distributed level. These things happen at the code level. And you define it and say, oh, this is what a key value server looks like, just like we were talking about, but now down at the code level. So right now, as things stand, like right at this moment as we're doing it, what it looks like is there is some custom code. A lot of people have this right now, where we have what's called Wasm Bus RPC that's sitting in this KV counter code we're talking about. And that code has all the magic to handle the stuff coming in from that lattice and sending stuff back out to the lattice. But what we really want is for true flexibility between platforms. We don't want a walled garden. And that's what we have been really been working with the community. A lot of us have, who are in this community space right now, to make sure this component model becomes reality. And what it's going to look like in the future with this component model, which we'll be able to actually demo pretty soon here, is we're going to split things out. So now we have something that implements the HTTP server interface and knows how to forward the requests into user-provided code. And the same thing, we have one that knows how to take a key value request and send it into what we're expecting for our lattice to do it. And so what the net result of this is you could have something running on one platform that's not Wasm Cloud, take that exact same WebAssembly module and run it in Wasm Cloud with 0 changes, as long as it's the same contract. And we're already collaborating on shared contracts such as key value and HTTP server and those kind of things with the rest of the community. And the other thing I want to note is that in both of these cases, you're not locked into the contracts we provide. You can create as many custom contracts as you want. We'll actually show you what we've done for real inside of Cosmonic with this. But you can create whatever contracts you need to make it work while still using all these standard contracts. So I just wanted to call it that this stuff that's coming in the WebAssembly community right now is the same idea, but at the code level. You're able to swap out exactly what you're going to have. If you need a specific implementation for your company, you swap that out. And there's no extra effort for the actual business logic of your code. So this happens both at this code level and with Wasm Cloud at the distributed level. And so I just wanted to point that out. It felt like a really good point here to really just show, like, this is something that we're really hoping can change the way we write these applications and the way we move them around. So with that, we want to go back and demo a little bit more. We just want to take a brief interlude here, but we're going to show you something that's even cooler that uses a real pattern with a to-do app. But with a real architecture pattern you're going to see for actual applications you'd want to build for a big company. So we'll go ahead and show that now with some more.
Yeah, so if somebody comes to you and they're talking about some application that they're building and they pitch a RESTful API service that's distributed across different availability zones and regions for high availability, but then ends up storing data in a centralized data store for easy management and access and backups. It sounds, I'm describing a pretty normal application that you would build in order to get things done. And so we're doing this with the kind of the front end of a to-do app to show, that's really easy to grok. But there are distinct benefits to building this with WebAssembly and with this separation of capabilities. So what I didn't really talk about is I like to call this the application diagram. When we kind of blow this out into the HTTP server requirement, in this one we're actually using NATS as a message bus, to kind of do like pub/sub based messaging. That's also a very common cloud native pattern. And then again, store things in a key value store, but we could of course use like SQL or something depending on your data relations.
Yeah. Imagine that this distributed KV thing is a data processor. You fired off a message, you fired off some data, you need it to be processed before it's stored in a database. Completely normal pattern you'd expect to see.
Yeah, and so I really like to call this the application diagram, because if you come up with an idea, this is what you could sketch on the back of a napkin at a little cocktail hour and say, here's my, I got this idea for this application, here's what it's going to kind of look like. But the really cool thing is when you build applications in this way, this can be the application diagram and not the architecture diagram, not the things where you say, point out, like, I'm going to use this specific database. And so this same diagram can be blown out into, an architecture diagram like this, where I'm running some resources in one cloud, I'm running a couple of different replicas at, I'm going to use the edge as a buzzword, but I actually have a Raspberry Pi running at my house in Washington, D.C. that I have connected. I have a Docker container that's running. I have a cloud instance in Google Cloud that's just like running on a VM. We can really blow this out into a wild, I did a little talk on a similar architecture. I called it wildly distributed WASM. And again, this is just to show the kind of flexibility that we come to expect from applications today, that sometimes you have to architect your entire application around. Like if you're going to run in multiple availability zones or in Kubernetes and in multiple different clouds, you have to build that in from the beginning. It takes a lot of effort to set that up. But building applications in this way, it takes no effort. You can use the same application diagram, the same components, and it works all the same. So let me show you this application, and then I'll go into code right after. So I have this whole thing running, again, kind of connected into the same type of system. But you can see my different services here. I have the To-Do API gateway. It's a RESTful API. It actually implements the To-Do backend spec. I don't know if you all have seen that before, but it's kind of like an attempt to be able to compare different languages on how they compare or how they make a very similar pattern. And then I have this distributed KV module, which takes messages that are sent over a message bus and then stores that information in a key value store. And that's actually spread across a variety of different infrastructures. As I said, I've got one host that's running. This is actually in my house in DC. It's on a Raspberry Pi. I've got this one host that's running in Google Cloud. That's on an x86 Linux box, different architecture, doesn't matter. I've got another host running in Cosmonic in the cloud. And then, again, this one I said cloud equals Docker, but it's really just a Docker container that I'm running on my local machine in the conference. I always like doing that because it's pretty fun. But if we kind of drill into this, I've got a couple of instances of this distributed KV microservice. I've got a couple instances of the To-Do API gateway, distributed KV, the actual UI that it's fronting, kind of spread all across all these different instances. And again, it's kind of wild, but a really practical example of this would just be, hey, take my service that I wrote and run it in 3 different availability zones so that one can go down. Now, what this actual application ends up looking like is, let me find it. If we take a look at this To-Do app, we can see that it's a to-do list. We have a couple of different things. I had a to-do to bring this up at scale, so great, and go ahead and cross that one off. I got to toggle light and dark mode, prepare your eyes, and then we can turn that off. We can delete a task, all those things, and the really cool thing is that this is all being kind of persisted in the key value store at the end of the day. So this is a real kind of application architecture. You don't have any idea because it doesn't depend on it from the business logic perspective that it's running in all these different places, but really what this adds is a greater amount of reliability, and it's really just cool that I've got some instances running on a Raspberry Pi at my house. It's really fun. So, as I mentioned, this has the flexibility of automatically failing over to available compute. The really cool thing is that I can take something like this cloud instance that's running in GCP, or why don't we do the Raspberry Pi? Like, right, this is a little edge device. This is something that's running in my house. Like, imagine my dog walks over and trips on the cord, unplugs the Raspberry Pi, and it goes away. Like terminating this or an availability zone going down in the cloud, the really cool, oh no, we'll see if it actually gets there. The really cool thing about this is that it will continue to work all the same. It got there. It'll continue to work all the same. I can refresh, I can get all the same data, and this is really just something that, the point is not to talk about how wild this is, it's that this is really how easy it is to build a resilient cloud-native application with WebAssembly today. It's not just something that's built for some toy demos. So one more thing that I wanted to just kind of drive this point home, we talked a little bit about how the visualization that you're looking at is kind of a way to just kind of look at the way that these services are architected. Now at Cosmonic, we actually built our backend for the platform on Wasm Cloud. So the whole backend for this platform that I've been working with is written with WebAssembly modules and implementations of services. And we talked a little bit about this in our last talk at the last KubeCon that we spoke at. But for example, we have some services that deal with secrets. So locally, we implemented it using Redis, bless you, and then when we actually deploy that up into the cloud, when we work with actual customer secrets, we use an implementation with HashiCorp Vault. That can all just be swapped out at runtime. And I wanted to show you kind of this wild diagram of visualization of services that are running this backend. It's an event source system. So we are using this to do very real applications now. We built a platform on top of it.
Yeah, all these interactions that you just saw Brooks do, like on this canvas, and all these things where you're like hitting these APIs and whatnot, all of this is done with WebAssembly. I just want to drive that home. Like this isn't a toy. We showed a toy app because it's funny with the to-do, but you can actually build real things with this. And everything we're running, we're our own customer for that reason. Cosmonic is our the first customer of Wasm Cloud because we want to be able to use it and make it better for the community. And so we're building something that's very real on top of this. That's a whole mixture of APIs and event bust things and like Brooks had mentioned, event sourcing. Like there's all sorts of patterns that we're running on top of this. It's not locking you into doing functions as a service. If you want to do a functions as a service type thing, you can do that with Wasm Cloud. You're doing something like a microservice-based pattern, you can do that with Wasm Cloud. All of these things are doable and you can do it right now. And that's what we wanted to show, that this isn't a toy anymore. 2-3 years ago, a toy. Nowadays, like all of these things are not toys. You can actually build something real with it. Right now.
So Taylor, we've shown a few applications, right? Shown a few patterns, talked about some capabilities. You know, how do the beautiful people in the audience take this home and like actually get to do something? Yep. What could they do?
This is the what to do section. So what could you do now? And I'm taking this from if you're just playing with this on your own, you can do whatever you want because it's your own time. But if you are like you know, you're just looking for, you know, that stress relieving project at work. You've got your other work done. You wanted to try something new or experiment with something. These are some recommendations that we've seen be very successful. The first thing is that you could do some sort of basic data or image processing type of thing. That's a very like standalone service. It can run on its own. You can run that in Wasm Cloud, and that's great. You can also do one small part of a service. If you're already planning on refactoring something or trying to refactor something, you could take that single part of the service and move it over. My talk yesterday was about how you can do that if you're running in Kubernetes and then also run it in Wasm Cloud. So go check that out if you want to see details on that. But like you can run one small part in Wasm Cloud with that newly refactored thing, and it's going to run a lot smaller and cheaper because of all the benefits of WebAssembly.
Yeah, we saw a few companies that were running services like this in Kubernetes. It was really low utilization. It was a really simple business logic, and running it in Wasm allows you to run it a lot cheaper.
Yeah, like I said, that scale really kicks in when you start looking at it. And when you have the last thing is obviously like a full stateful application. If you have a greenfield thing you're looking for, you can actually start to do that and build it from scratch using the different providers and things that are out there. And you're not, like I said, you're not locked into it. If you need a key value store that's like a custom key value store inside or like performance tuned one that you have inside of your company, you can write a provider that implements that interface and just keep coding against the exact same key value interface, whatever it might be depending on your needs. So that's kind of in order of easiest to hardest to do, just some stuff you can try. But what you can also do is go to our Wasm Cloud doc site. It's wasmcloud.dev, and you can see a bunch of examples there. We also have a bunch of example applications, and it's geared towards Cosmonic, but we have them on the Cosmonic doc site. We have some things to build, and it shows you a bunch of different architectures of things and walks you through it. Most of those things, although it's like saying, oh, here's how you run it on Cosmonic, will run exactly the same on plain Wasm Cloud, like open source. So with that, we're going to go ahead and put these up here in case you're curious and want to talk more to us. We have our Slack link on the left is the QR code. We're very active there. We're always looking for people to chat with, and you can let us know what you're trying out, what you've run into. And on the right is the QR code to our main landing page repo. That will have links to all of our other repos where like this Wasm Cloud host lives, the capability providers, all that kind of stuff that we've defined. So with that, we'll go ahead and open up some time for questions.
Yeah, I put in a slide for that. Just want to call that out, but I'm going to put the QR codes back so that anybody can scan. All right.
Yeah, go ahead and run it.
So my question is, this naive WASM question, how do you do configuration management? For example, when I spin up a web server or an Nginx, I have to configure it initially. And is this all done dynamically? When you spin up a WASM, is it kind of like a blank slate and you have to make calls to actually configure it? Or is it the links that you do is configuring it?
Yeah, not a naive question. Is this still coming through? I tried to put
Yeah,
it.
go
Yeah,
ahead.
we're trying to
Okay,
both
great.
be able to.
Yeah, not a naive question. Yeah, so the really cool thing about this kind of link and capabilities model is that none of those things that you're configuring in Nginx are actually compiled into your application itself. Those things are all kind of configured at runtime with that link. So all that kind of configuration you would do for like an Nginx is done with that link, and that can be done. I'm doing everything imperatively in a UI to demonstrate, but really we have a declarative model that we use, again, open application model for, and you would essentially put that configuration in a config.yaml type thing and apply it.
I'm kind of confused because I think that WebAssembly gets started like a JavaScript type thing inside a browser. There's some things you can't do in there, like you can't have threads and synchronization. But Rust has threads and synchronization. So what would happen if I compile a Rust program with all of this stuff and try to run it in a browser?
That's a good question, actually. So it's probably actually not going to compile in Rust. And I think a lot of other languages will tell you that. Or it might compile, and when you try to run it, it'll give you a runtime error saying it can't find function something that allows it to be able to run. And so the way it works right now is you called out one thing that I didn't say in one of the disadvantages, is it is single-threaded right now. And that's true in the browser or on a server. But you can work around that because number one, it's so lightweight that you can just spin up a whole bunch of them simultaneously handling the request. But WASM, like threads inside of WebAssembly, are already like in flight. There's people who are actively working on that and getting it working, so that then that code will probably work just fine.
So synchronization of threads, if you're not in a browser, will work eventually.
And
Yes.
Just in case the recording didn't get that, the question was if synchronization of threads may not work today, if eventually the work it may compile and work on the server.
Yeah, and that's correct. Yeah, awesome, great question.
I had a bunch of questions, but they asked a few of the ones I had. But like going from Rust, anything to WASM is a compile, not a transpile, or
Yeah, it is a compilation target. So like when you're building it, it's like saying, so in Rust we build with target wasm32 WASI. And so
Okay.
like that's an actual build target. And same thing when you build from Go or anything, you're building to a specific target because it is a binary, but then it passes through a last compilation step when you run it. And like I said, that's configurable at runtime. You can use AOT, JIT, interpreted depending on the requirements of your platform.
okay. And then what actually makes the compiled code work on any hardware?
The thing is here when you have a WebAssembly binary, that's not the actual artifact that you execute on the system. You run a WebAssembly engine, which then is responsible for running that. So
And that's,
you can.
sorry.
Oh, no, you can kind of think about this like a container runtime. Like the container runtime is the thing that runs on the system and it's executing containers. The WebAssembly part, the WebAssembly is just kind of like it's a stack-based virtual machine. So it's a set of instructions that runs in a WebAssembly runtime. Do you wanna add
Yeah,
anything
and that's
on
what I was thinking. It looked very similar in terms of a model of how it runs. It looked very similar to either like a Java virtual machine or the Gecko engine in JavaScript.
that? Yeah, some WebAssembly people, including Taylor, might hate me for saying this, but I think it's a decently apt comparison to talk about Java because it's the Java virtual machine runs on the platform, and then your Java bytecode is not specifically tied to a platform. It runs on the virtual machine.
I see. Okay, and then another question I had is in regards to the capabilities part. How were you? Because it looked very easily in your demo here that you can hook things up, but I didn't see anything where it went. Wait, can you? Are you sure you want to do this, or did you really want to talk to the? So,
Yeah.
and then the other part is if you have, say, tens of thousands of these modules, saying, do I want to do this? Do I want to do that? Or is there something else that says, it's like similar to like a console where you can say, well, this is recognized as this service, and by policy, we say, yeah, that can connect to that.
So actually, that's a really good question. So the only thing you have to manually do, or through like the declarative definition stuff, is to declare that link.
Okay.
But outside of that, we have a huge defense in depth thing. We've given multiple talks on this. Kevin, one of our coworkers and our CTO, he gave a good talk on this at Cloud Native Security Con. Yeah, and so essentially what it allows you to do, and he's actually going to show you what this looks like, is every single module and every single actor and every single provider is signed and has to be trusted by the host. So and not only that, every single invocation between the different things is signed. So if some bad actor tries to put in something that they're not supposed to, they're going to just start, if they do manage to link it, which is hard enough as it is, then they end up they'll get invocation failed requests because the signing isn't there. And all this is done pretty transparently for you. And so we have a massive set of defense in depth that was built into Wasm Cloud from the beginning, specifically to handle those kind of concerns.
Okay.
Yeah, so you can essentially, you can set up a policy service to add a list of essentially allowed capabilities to manage. I used to do a demo where I would have this, so every single WebAssembly module you deploy has this list of capabilities. In this case, it's the officially supported HTTP server key value store. That's all available just by inspecting the module before you even run it. You don't need to, you can tell exactly what it's going to do. This module can never make an HTTP request on its own. I used to do a demo where
But that can be externalized too, right? You can, or
yeah.
I want to say console, but that's the most common one I know, or something like in Kubernetes where like a Calico or something like that, where you when the module comes up, hey, I'm the service, and it basically says, well, okay, I recognize you, and by policy, you are allowed to talk to it because we've done that externally, in another piece of software.
Awesome. Thank you. I thought I saw one more question out there.
I know you had a question.
Yeah, yeah.
You were technically the first.
So the Cosmonic UI, is it operate 100% over Wasm Cloud APIs, or is it manipulating the IDLs directly and submitting it and the YAML? And basically, how much does it manage outside of Wasm Cloud, or is it just a dumb, hey, I'm just using I/O via the API calls?
Yeah, so I actually gave a talk on exactly how we built this at KubeCon Detroit. I think, yeah, KubeCon Detroit. You can look that up, but the API and the UI are like just normal JavaScript, and then like an API. I think we built the API in Elixir. After it hits the API, which is just doing I think GraphQL, and there'll probably be some REST stuff in the future, my guess, but that stuff gets translated into stuff that is then pure WebAssembly after that.
Yeah, Wasm Cloud API calls.
Yeah, Wasm Cloud API calls. So it all goes into that, and then the only other thing that's not WebAssembly after that is the infrastructure we're running on. And even that, a lot of that, we spin up through calling WebAssembly stuff that uses contracts to call the right things for the infrastructure. So there's just a little bit of stuff at the front that isn't WebAssembly, and then the infrastructure itself, and everything else on the platform is WebAssembly running on Wasm Cloud.
Any other questions? We are reaching
time.
the end.
Well,
Sweet.
thanks everyone for sticking around tonight. And then, we have one more question.
We've played around with your WebAssembly application, seeing how many requests it can take. We've hit it with about little mini CTF challenge during your talk. We've hit it with about 1,000 queries a second.
Nice.
So go ahead and refresh your thing.
Nice.
Okay, but just refresh a couple times and maybe you'll get it. But anyways, your WebAssembly is very variant tolerant, and clearly this is like a single core, a single threaded application.
Mm-hmm.
So clearly the lesson learned here is use WebAssembly and scale your stuff on Kubernetes, because clearly this tolerates way more than any Node application I've ever written. So yeah, thank you so much.
Thanks for checking that out. Awesome.
Yeah.
Thanks everyone. Have a great night.
Thank you all.